All right, so this would be class 22, and this is springs continued. Things that you'd want to know about springs. One of the things we want to know are the end conditions for the coils so that we can count the coils. And so this is an important table in the book. We want to probably find that. I could go look for it right now. Maybe I will do that. So getting ourselves acquainted with the book is an important part of the course. So we will open up our 10th edition of Shigley, and we will go to our springs. Let's see, springs, Hope Springs Eternal, mechanical springs, and we cycle through there, and right there it is, table 10.1. Well, it must be important because it's the first one. And what we find is we have these different end conditions, and we want to try to explain what they mean by these end conditions. By the way, it's a little confusing here because I was confused by this. These are four different end conditions. They're using this. Figure for multiple purposes. One is to tell you what a right hand and a left hand spring looks like. Thanks a lot for that. And another is to tell you what the end conditions are. And then this over thing on to the left serves no purpose. So that just means the spring continues. All right. So all you should care about is the fact that this is a plain end. This is a squared or closed end, and I don't think they mean, I think they just mean there's two different ways of naming this, right? So they said squared or closed end means either way you want to call it, it's the same thing. What they've done with the plain end is they just cut the coil, right? They have a really long coil and they cut it someplace and they delivered your spring and said, here you go, here's the spring. The trouble is it will only stay at one point, right? It'll touch only right here onto whatever surface you put onto it. One thing that you could do is you could bend that little last coil in so that it closes it, right? And that kind of in turn kind of squares the face off. So now at least has a little bit of an edge to sit on instead of just a single point. Or what you could do is you could close it like that, and then you could take a grinder and you could grind off some more. So now you have a lot more of a flat area. Or if you're just really lazy and didn't feel like doing that, you could just grind off the thing, and now it's going to come to like a real thin point right here. So let me show you what that looks like in a couple examples. I think these are all really this C right here. It seems to be the common one right here. So here we go. Okay, here we go. So you can see the end of the spring right here. You can see he's kind of closed. He's a little bit ground. They ground off a little bit right there. But for the most part, he's kind of closed. Right, and I'm turning this thing, and you kind of see the same thing over in this end right there, right? So there's a flat area right here for this thing to sit on. Here's one where they did a lot more grinding onto the piece, right? You can see that they closed the thing, right? So it doesn't have the same gap right here as it does in the next coil down. This has a much more of a flattened area for to lean against. This one, I thought this was this is a much larger diameter spring right here. And so you could see there's that flattened area, but also you could see that it's closed. Right? Whereas this guy right here, they didn't bother. They just closed it, right? They didn't bother to grind the thing off. Wasn't worth it. This is just a cheap spring. I think I bought it at Home Depot. I'm not even sure what it's made for. We don't need to see it inside by nose. That's fine. So anyway, there's a bunch of different springs. It's Hope Springs Eternal. Same joke, keeps using it over again. So in this table that we care about right here, that's what the figure is. It tells us, we say when we have plane or plane and ground, that's going to be this guy right here. So no, this guy down here, D, right? So I don't know why they didn't put this guy in order of the figures that they have above, but they just didn't. And so you have plane up here. You have plane and ground, which is down here, D. You have squared or closed, which is this guy. And then you have ground and squared and ground. That's this guy right here, right? So they went zigzaggy diagonal. And so what was useful to us is they have the number of end coils are determined by that. Plane doesn't have any end coils. But plane and ground right here, this guy right here, you could consider that that's going to essentially be one end coil. And we'll talk about what end coil means here. And then squared or closed or squared and ground, either this one or that one. We're going to say that 2 of the coils are going to be ineffective. So, and this is kind of a weird one where they kind of go backwards, right? They tell you the total number of coils are equal to here. What they really should say is the number of active coils will be the total coils minus the end coils. That's what they really mean right here. But for whatever reason, this table has this kind of weird. And so if we go up to the very beginning here, this is counting the coils is an important task that we could do. Right, so they go 1. So they're starting right here, and they're not counting this coil right there, right? So, or you could say that there's a half a coil right there. We're only going to count when that happens, right? So 1, 2, 3, 4, 5, 6, 7, and then kind of another one right over there inside. So they're saying that's 7.5 coils total. But in terms of active coils, right, because this right here, you can tell that this is squared and ground. If you're talking about what's going on inside this piece, you can see that's a coil 1, that's a coil 2, that's a coil 3, that's a coil 4, that's a coil 5, there's half a coil. So there's the number of active coils is really 5.5 right here, right? Although there's 7.5 coils, there's only really 5.5 of them are active and actually doing anything. Only 5.5 can absorb energy or can contribute to the deflection. So that's what we do here. We want to go. So one of the first things we often will do, I just put these in order in the book, but we will go to this section and figure out, we'll count the coils, and being very careful, we go ahead and count them, and then all the ones, even if they seem like, and include partial coils, right? We'll just start where it starts and end where it ends. And if it doesn't wrap around all the way, then that's just maybe part of a coil. And then we figure out how the ends are treated. And then we subtract off the end coils, and we have the total number of active coils. They also have a couple other things that might be useful. You might need to go backwards if you actually could measure the free length, and you know the pitch, and you know the diameter right there of the wire. You're able to you'd be able to find the number of active coils. Or if you needed a certain number of active coils and you knew what the pitch was going to be. And by the way, the pitch is simply the distance between coils, right? Or not between the coils, but from one coil to the next, right? So you want to start in the center of a coil and go to the other coil. That's going to be the pitch. You want to start at the end of a coil, but and then go to the end of a coil. Doesn't matter. It's still going to be the pitch, no matter what. That's just the idea of the pitch, right? But if you want to find these things in various ways, one thing we often will find is the solid length. And that's just like, you could, it's really the easiest over here, right? The solid length, for the squared and ground, it's just going to be the, wire diameter times the total number of coils, right? And I think in the other video, I tried to crush one of these coils and nearly sent the thing flying. So you would see that number. That's one of the very first steps right here. It says at the bottom is to determine the number of coils. And here's a manual. Here's a catalog, engineering part of the catalog from Century Spring. You could look this up, and you can see that they have a lot of the things that we would want to know in here, including, by the way, they decided to use the wall curvature stress correction instead of the Bergstrasser. We're going to use the Bergstrasser, but because that's what Shigley uses a lot. But anyway, you can see that this is all contained in here. And for some silly reason, they decided to write stress with a capital S. Those maniacs. Anyway, continuing, and here is also a catalog page from Century Spring, and where we can find a whole bunch of different information that we care about, like the spring rate. That's the stiffness. We are cataloging it, and by order of the outside diameter. They also have the various, and then going down by free length of these off-the-shelf springs. They also give you the inside diameter, but over here where we got the wire diameter, right? So that's something we want to know. The total number of coils, the kinds of ends, right here. They have closed, open, closed ground and open. Sometimes the closed and ground CG are right there, so you know that exists. We also have the material right here. We'll see that in a minute. Over here too. Those are all materials. We'll talk about that in a second. And they already give you the solid length, and they give you like a suggested maximum deflection and a suggested maximum load. So these are all things that we're going to want to know as part of a spring if we're going to pick one out from a catalog. But we want to be able to use them for various things. So I'm going to go over the example here in a minute in another video. Let's continue with the topics. Stability. This is just like a column, right? And a column can buckle. And I did this in the other video, but let's right here. I guess I'll keep it. Whatever. I should be throwing it away. But we have this long spring right here. This slender spring, and if I try to crush this thing, you can quickly see that it's going to try to go outwards, right? Even my best attempt can send the thing flying, right? It's tough. Well, that's the buckling. We have to be concerned about the thing buckling. An easy fix to that is just to put something inside it, right? And now you don't have to worry anything about the thing buckling, right? But you might have to worry about, I don't think in this case, but the diameter can change when a little subtly when you're squishing it. But I think it actually gets bigger. I don't know. Anyway, is something to consider. Buckling can be an issue to the thing, and the end conditions of the buckling, whether there's a pin right there, or whether they're flat plates that are constrained to be flat. The truth is, though, that this isn't a topic I like to deal with in springs because it's difficult to relate it back to the fundamentals. Because when everything's said and done, they just use in the book this equation right here. It's really boring, right? So that's just keep the overall length less than 5.26 times the diameter for regular ground ends, right? Which is kind of typical. But I'd rather be able to like derive this and use this with buckling stuff that we might have learned in 370, but can't quite do it. They don't give you enough information. They kind of use more of a rule of thumb kind of a calculation. Those are no fun. This is an interesting thing. I believe I pick it up into the next class, but there is this one website that I can show you. They start to show these ranges of usable parameters, and with that kind of idea, we can start to narrow down where we're going to pick a spring. Now, I think this is the last topic I'm going to cover in this video. We have spring materials. An interesting thing is that the material strength of a spring is not just dependent on the on the material, but also on the wire diameter, right? And so empirically, they have found this exponent and coefficients right here of A, right? So that we find the ultimate strength by coming to this table, and for a particular material like music wire is one of them. And you'll note that in our catalog right here, music wire was one of the choices. Oil tempered was probably another one. You also had stainless steel. There's also hard drawn, right? So that was in the manufacturer, but also excerpts out of Shigley right here. We have hard drawn, and we have oil quenched and tempered, and we have music wire. So you can maybe make the jump and say, hey, I think those might be the same material properties that we could use. And then so we have these parameters that we use with the wire diameter. But we also, this is the ultimate strength, but we know that our stress was shear. So we need to relate them, the shear strength, to this ultimate strength. And we already know that for static things that we had been using the shear yield was going to be 0.577 times the yield strength, right? But this is the ultimate strength, right? So that's not necessarily, this is something that we knew empirically to be true. This is something we knew from first principles to be true. But we want to actually relate the ultimate strength to this right here. And we find there's actually a range of some things that we multiply to the ultimate strength to get that turning it into shear stress strength, which is what we want to compare. And that usually, so what we generally do is we'll use either 45 or 50, and that's all about whether the set has been removed, right? Before set removed and after set removed. And so, by the way, this also includes the Bergstrasser thing in there when comparing apples to apples. By the way, I should also, before I forget, mention that we often will need the elastic modulus. Well, actually, we need the shear modulus. We don't really need the elastic modulus for anything. We need G, the modulus of rigidity. Ooh, I like that name. And you notice also that it is partially dependent on ranges of wire diameters, right? But here's your music wire, here's your hard drawn, and here's your oil tempered, right? So those are like the three ones that we've been mentioning. And then, so we might want to take our process of finding our strength is to find the ultimate strength and then apply either 45 or 50. We will not remove the set. We'll keep the set in place. Now, set removal or presetting is a process used in manufacturing a spring to induce useful residual stresses. And the spring is made longer than they need it, and then they compress it to the solid height on purpose so that it yields, and then it doesn't bounce back to its original length. And this sets the spring and to the required final length. And this will induce residual stresses that are in opposite direction of the ones that you'll see in service. And you can actually get some benefit from this, but it's not good when you're worried about fatigue, right? So I talked a little bit about that in class. So the rest is going to be examples for this class, and I think we'll do something else in the next class. So I could discard all of that. And how long this video came out? Came out to 16 minutes long. That would have made the other one like 45.